You're now going to take a look at one of the greatest applications of integration, and that is finding volumes. Now let's start with the volume that we actually know. Okay, let's consider the volume of a cylinder. Okay, so here we have a cylinder, and it's going to have some height h and radius r. Okay, so we have a height h and a radius r. Now, how can we use integration to find the volume of this cylinder? Well, integration means summing. And so the idea is you want to sum a bunch of something to get a volume. Well, this is kind of a nice looking picture because you have all of these circles. And so if you sum a bunch of circles, right, you stack them up and you add them up, the result is the volume, right? This works because what you have here, you have, say, an arbitrary circle like this one, right? And so that was like the ith circle, and we can get its area, and it's got an infinitesimal height, right? That's the whole idea. Each of the circles has an infinitesimal height. Now, if we consider this in terms of, say, an x and y coordinates, then the height would be like a dy, okay? And so what we're summing, okay, remember integrals mean sum. We're summing a bunch of circles. They all are pi r squared here, right? Each circle is the same circle. And we're summing them from what to what? We're summing them from 0, right? If we imagine, this is our like xy axis here, and we would have like, this is our x-axis and this is our y-axis. We have it starts at 0, and we go the circles stack all the way up to height h, okay? And so when we're summing all of these circles, what we're really summing, you can think of them as sort of like discs. And these discs, they're circles with it's kind of like this dy, this tiny little thickness to it, right? And so it's going to be all these dy's. Okay, so this sum, this integration will give us the volume of a cylinder with height h and radius r. So let's go ahead now and do the integration. We get pi r squared y, because we're evaluating dy, it's just y. That's the only, see, we're not integrating the r, we're integrating the y. And there's no y, so it's just like, if you integrate 3, it's 3x. If you integrate pi r squared with respect to y, it's pi r squared y. Evaluate from 0 to h, the 0 goes to 0, and you do get the pi r squared h, which is the volume of the cylinder. Okay, so pretty cool. And let's go over some additional examples. And we can look at this in a lot of different ways. Okay, when you're doing integration, there are two different types sort of that you see. You see these kind of like, what's the volume of the shape, which we kind of started with and put our own axis on it. And then you see another kind, which we'll look at next. And that might be that you have some kind of a curve, okay? And so let's take the curve, y equals the square root of x. And what you often do with this curve is you rotate it around something. And so in this particular case, we're going to rotate it around the x-axis, okay? So that's kind of interesting. And if you rotate this around the x-axis, you think, well, what do you get, right? What is this shape? Now, when you're doing rotations, I would think about it as sort of like individual points. In this case, let's go like, say, from 0 to, you can imagine maybe this is the point 4, 0 to 4. Okay, so when you rotate a point around an axis, it's a circle, okay? Circle up here. And so this is going to be circular. right? It's like for me, I mean, I can't really draw accurately the three-dimensional shape that it's going to be, right? It's sort of, I mean, I can try a little bit, like it's going to come down, and then, you know, if we rotate this, it's going to be circular, so it's hard to sort of do it right. Like, do I go this way or this way to make it? I'll just kind of do it like this. You know, you have like this sort of fairly thin, centrally thin width, but you have sort of like a circular shape like this. Okay? Now, note that this is the same as x equals y squared, and so it is a paraboloid. Okay, so what's the volume of this thing, and how do we figure it out? So, what we can generally do on volume is the following. For volumes, we are summing the area, S for sum. The integral note is sort of like an elongated S, so, you know, you make it more elongated. Okay, so we're summing a bunch of areas, okay? And in fact, I actually write it like that. It's the area, but it's the area times the differential. And what the differential is going to depend on your orientation, okay? So what you do is you take an arbitrary cross-section. And so in this one, if we take like an arbitrary cross-section, it's like somewhere in the middle. Okay, what do we end up with? We end up with some circle, you know, that looks something like this. And what we need to figure out is what's the thickness of this circle, right? Well, if you have a bunch of circles going left to right, each has a thickness of dx, okay? And so this will work for the volume of sort of any function that is rotated around the x-axis. You're given y in terms of x. And then the next question is, what is the actual area of, say, the arbitrary circle? Okay. Now we're going to be summing these circles from 0 to 4. And a circle we know is pi r squared. So you can even write that as pi r squared dx. Okay, so what is r? We need to find out what r is in this function. So if we look at the radius, right, that's the radius. It simply goes from the x-axis to the y value, okay? So all across this function, the radii are always the square root of x, right? And so we can rewrite this as the integral from 0 to 4 pi r squared here. You know, you can basically say, I mean, r equals y, so this is equal to r. So r equals the square root of x. And so if you square that, that's just x, right? And so it's pi x dx, because r squared is x. And now we're ready to integrate because we have everything in terms of x. We can pull out the pi. So we get the pi, we get x squared over 2 as we integrate, evaluate between 4 and 0, and we get 8 pi. Okay, so the volume of this paraboloid happens to be 8 pi. Okay, let's look at another one. For this next example, let's consider, okay, we have a curve, and again, we'll just look at the positive part of the curve, and we'll go with, say, y equals x, and then between y equals x squared, okay, and we're going to look at that shape now rotated around the x-axis. Oh, okay, this gets to be a little bit interesting. So we've got two curves, and we're going to rotate them around the x-axis and figure out what's the volume, right? Again, kind of weird to draw here. You know, it's going to sort of like, if you're rotating it, it's going to be kind of symmetric, but do note, like, it is a volume, right? This is showing kind of some of the rotation piece, and this is sort of weird looking. So what's actually happening here? Okay, what you have, again, what you want to consider like these arbitrary cross sections. Now, why do I keep saying arbitrary? It's because like there's special ones, like the endpoints. You know, it's like those are special. You don't want a special one. You want sort of one that's kind of like in the middle-ish, one that will be just like any other. And so rotating around, it's still going to be circular, but if we look at, say, this cross-section, and we rotate it around, right, we've got these 2 points rotated around, what do you end up with? You end up with what's called a washer. Okay, so a washer looks something like this. Got a circle, and then you've got another circle. And the idea is you want to figure out what is the area of this shape. So the area of this shape, generally speaking, you've got 2 radii. Okay, you say the big one is big R, right? So we'll call this capital R. Then you have this other one, little r. And so the area is pi r squared minus pi r squared. Right? Because you're taking the larger area and you're subtracting the smaller one. Okay, so that is what these cross sections end up being when you have basically a sort of like 2 curves and you rotate them and you get a washer is your cross section. Okay, so we're going to write out the volume. This one, so we get volume is the integral of, and what are we going from what to what? Okay, we're going to find out where do they actually cross, 0, 0, and 1, 1. So we're going from 0 to 1, and then it's just the area, and I sometimes like to write out just the area to make it clear that that's what it always is, and then because we're summing a bunch of washers and they have vertical orientation, we're summing across x, it is going to be dx. Okay? And now we can put in the formula for area, but note it is this, right? It's this thing. So we can pull out the pi. Okay, so we've got a pi out here. And then we still got the 0 to 1. And the area is going to be pi, and I'm just going to, I already put the pi in. It's just going to be big R squared minus little r squared. Big R is the one on top. Okay, it's the height, it's the y, it's the x. So big R is going to be simply x squared. And little r is actually x squared. Okay, that's the lower one. So we square that x squared, you get x to the 4th. Okay? So again, it's just pi r squared minus pi r squared, but big R is little x, and little r is x squared. It's evaluated at dx, and so now we can just integrate, we get x cubed over 3 minus x to the 5th over 5. We got to put the pi in there, and we're evaluating that from 1 to 0. So the zeros cancel out, we get a 3rd minus a 5th. Okay, so 1/3 minus 1/5, all times pi, and get common denominator 15 multiplied by the other terms. So we get 5/15 minus 3/15, and we get an answer of 2/15 pi. Now, let me just put this into some context here. Calculus allows you to find the volume of anything. Okay, so this is pretty tremendous. Just like with area, right? Calculus allows us to find areas that are all kinds of like interesting curves and this and that. And same thing with volume. So the idea is you're simply summing a bunch of areas. And what you'll see commonly are examples like these two, where you have equations and you get the curve by rotating. But you also might see ones like this one, where it just says, hey, find the volume of a particular object. In that case, it can be beneficial to put in your coordinate system. Now, it's not always dx. This one's a dy. It depends on which way you're stacking. Here, if you're stacking vertically, think of these disks as having infinitesimal thickness. They each have a vertical thickness of dy. Whereas these two, we're stacking left to right, and so these each have a sort of a horizontal thickness of dx. Now, is it always a circle? No. Okay, but it often is. When you rotate around, which is common in calculus problems, it is a circle, but you will see other problems where you can have other cross sections. If your cross section is a triangle, you're not summing a bunch of pi r squareds, you'd be summing a bunch of 1/2 base times heights. If it was a bunch of rectangles, you would be summing a bunch of base times heights. So it does depend on the context of the problem, but I think it's amazing because calculus allows you to really figure out what absolutely any volume is if you can just put it into context.